somewhere in the silent abyss of deep space, the James Webb Space Telescope captured something that should not exist. It was not just another distant galaxy. It was a fully mature, spiral-armed structure shining from a time when the universe was still in its infancy. By every known law of physics, this object was impossible. Webb was built to glimpse the earliest stages of cosmic history, to catch faint glows from newborn stars and chaotic clouds. Instead, it unveiled a galaxy so old, so evolved, that its very presence rewrites the story of creation. Was this a mistake, a miracle, or a sign that our understanding of the universe is built on foundations far less stable than we thought? This is not just a discovery, it is a paradox, one that forces us to ask, what else lies hidden in the dark? And how much of what we believe about time, matter, and reality will survive the light Webb brings? Keep watching, the story is just beginning. The James Webb Space Telescope was not built to discover the impossible. It was constructed to refine our understanding of the early universe, to glimpse the faint light from the first galaxies that formed after the Big Bang. Its instruments were designed to peer through the veil of cosmic dust, using infrared wavelengths, allowing us to look farther back in time than any previous observatory. Scientists expected to see small, misshapen galaxies in various stages of assembly. Simple structures, chaotic in form, made mostly of gas and primordial matter. Instead, Webb detected a massive luminous spiral galaxy with a level of order and refinement that seemed absurd for its age. This galaxy, catalogued by scientists as an early universe anomaly, was not only large, it was structured. Its spiral arms wound gracefully around a bright, concentrated core. Star-forming regions were visible throughout its disk, indicating not only a rich supply of gas, but a system already stabilized by internal gravitational dynamics. This level of symmetry and coherence was expected only in galaxies billions of years older. The time frame in which this galaxy existed is perhaps the most disturbing element of all. Analysis suggests the light reaching us from this object was emitted when the universe was just a few 100 million years old, less than 4% of its current age. According to the standard cosmological model, galaxies require hundreds of millions of years to grow through mergers, gravitational interactions, and successive cycles of star birth and death. Yet this galaxy had achieved a state of maturity in what should have been the universe's infancy. This was not the messy clump of stars typical of young galactic formations. It bore the hallmarks of a mature spiral galaxy, including a well-defined central bulge and tightly bound arms. The distribution of stellar populations within it suggested stability and longevity, traits previously believed to require eons of evolutionary development. Its very presence raised urgent questions about how structures in the universe assemble, and whether we have fundamentally misunderstood the timeline of cosmic evolution. Webb's spectrograph provided more surprises. Chemical analysis revealed the presence of heavier elements that should not have been abundant at that stage. Elements like carbon, oxygen, nitrogen, and even iron, products of stellar nucleosynthesis, were detected in substantial quantities. In standard models, such elements only appear in significant amounts, after multiple generations of stars have lived and died, enriching the interstellar medium through supernova explosions. For this galaxy to contain them so early suggested either that stars had formed, evolved, and exploded at an accelerated pace, or that an entirely different process was responsible. The implications of this discovery were profound. If the chemical ingredients for rocky planets and complex molecules were already present in the early universe, it meant that the potential for planet formation, and possibly even life, may have emerged far sooner than previously thought. This forced scientists to reconsider the window during which life-supporting environments could have arisen. The story of cosmic history might not be one of gradual development, but of rapid, localized bursts of complexity triggered by unknown conditions. More astonishing still was the galaxy's rotational behavior. By measuring the light's Doppler shifts and internal motions, scientists found that the galaxy's spin rate was not only consistent with gravitational binding, it was remarkably stable. Its rotation curve followed patterns seen in present-day galaxies, despite the vastly different conditions under which it formed. This contradicted expectations that early galaxies should be dynamically unstable and dominated by turbulent flows of gas and dark matter. Adding to the puzzle was the intensity of the gravitational field surrounding the galaxy. Normally, astronomers assume that a significant portion of a galaxy's mass is invisible dark matter, which creates the gravitational scaffolding that holds galaxies together. However, in this case, the gravitational signature was oddly concentrated, with a sharp boundary rather than a diffuse halo. This suggested that either dark matter was behaving differently at that epoch, or that our models of its distribution were inaccurate in extreme early universe conditions. Equally perplexing was the galaxy's isolation. Most early galaxies are found within clusters or along filamentary structures that make up the cosmic web. Yet this galaxy appeared to exist in an unusually empty pocket of space, devoid of nearby companions or signs of past collisions. It had not been shaped by interactions or mergers with other galaxies, one of the main mechanisms believed to drive structural evolution. Its pristine environment indicated that its development may have followed a completely different path. Astronomers also took note of the galaxy's light variability over time. Subtle fluctuations in brightness hinted at the presence of an active galactic nucleus, a supermassive black hole consuming matter at the center. If confirmed, this would imply that not only did stars and heavy elements form early, but that black holes also matured much faster than expected. Conventional wisdom holds that black holes grow slowly, fed by surrounding matter over hundreds of millions of years. This object suggested a far more aggressive growth process. This raised even more unsettling possibilities. Could primordial black holes, those formed immediately after the Big Bang, have seeded early galaxies? If so, their role in cosmic evolution would be vastly greater than previously acknowledged. These black holes may not merely be endpoints of stellar collapse, but agents of galactic formation, shaping matter around them and accelerating the development of ordered systems. The discovery added fuel to a growing debate about the origins and purpose of these enigmatic giants. As astronomers worked to confirm and analyze the findings, additional anomalies emerged. Similar galaxies with the same unexplainable traits, massive, organized, chemically evolved, began to appear in Webb's deep field observations. What was once considered a single paradox was becoming a pattern. These galaxies were not randomly scattered. They appeared at similar epochs, suggesting that their emergence was part of a broader phenomenon rather than isolated events. This accumulation of evidence pointed to a crucial realization. The universe's early history may not be what we thought it was. Perhaps the formation of complexity did not follow a slow, methodical script, but occurred in short bursts under rare, extreme conditions. Or perhaps our entire framework, our measurements of time, distance, and mass, is incomplete, distorted by assumptions that no longer hold at the frontier of observation. The standard model of cosmology was not just being questioned, it was being stress-tested at its core. In the wake of these discoveries, the scientific community began to rethink its assumptions. The early universe, once imagined as a diffuse and slowly assembling landscape, might instead have been a mosaic of rapidly evolving systems driven by unknown rules. It was no longer enough to fine-tune equations or adjust variables. New theories would be needed, new physics perhaps, to explain what Webb was uncovering. For the first time in decades, observational astronomy was ahead of theoretical models, dragging our understanding of the cosmos into uncharted territory. The discovery of a massive, mature galaxy at the dawn of the cosmos did more than spark curiosity. It sent shockwaves through the foundations of modern physics and cosmology. The existence of such a structure so early in the universe's life directly contradicted our most trusted theoretical models. It raised a critical question. If this galaxy is real, and all data suggest that it is, then what else about our understanding of the universe might be incomplete, oversimplified, or entirely incorrect? The standard cosmological model, often referred to as lambda cold dark matter, rests on the idea that structure in the universe formed gradually through gravitational collapse. Small fluctuations in the early density of matter expanded over time, forming stars, galaxies, and clusters. These processes were thought to be slow, sequential, and uniform across the cosmos. But the Webb telescope's observation introduced a level of complexity, order, and chemical richness that could not have emerged from that slow build-up, not within the short time after the Big Bang when this galaxy appeared. This discrepancy called into question our interpretation of redshift, the stretching of light due to cosmic expansion, which serves as the primary tool for estimating the age and distance of celestial objects. If redshift is misunderstood, then our entire cosmic timeline could be skewed. Some theorists have begun exploring whether gravitational effects, unknown quantum interactions, or properties of space-time itself might distort redshift in certain contexts, leading us to miscalculate how old or far away an object truly is. Another area of scrutiny is the behavior of dark matter in the early universe. Dark matter is believed to form the invisible scaffolding that allows galaxies to grow by pulling ordinary matter into stable formations. But the galaxy detected by Webb seems to have formed with a level of gravitational cohesion that is inconsistent with known dark matter distribution. Could it be that dark matter behaves differently in the high-energy conditions of the early cosmos? Or might there exist additional unrecognized components to gravity, perhaps a modified theory of gravity that only manifests under extreme circumstances? This leads to one of the most daring possibilities: the need for new physics. The laws of gravity, as outlined by Einstein's general relativity, have stood the test of time for over a century. Yet, these laws have never been tested in the energetic and chaotic environment of the very early universe with the precision that Webb now makes possible. If gravity behaves differently at large cosmic scales or in different epochs, we may be witnessing the limits of Einstein's framework and the dawn of a new theoretical paradigm. The discovery also invites fresh discussion around the inflationary model of the universe. Cosmic inflation posits a rapid expansion in the first fraction of a second after the Big Bang, smoothing out irregularities and setting the stage for structure to form. But if galaxies like the one Webb observed already existed so early, it could indicate that inflation was more complex than previously assumed, or that it occurred in localized variable ways across different regions of space. Some researchers have even speculated about the existence of pockets, or bubbles of spacetime, where the conditions for galaxy formation evolved independently from the rest of the universe. In this context, the notion of cosmic variance gains new significance. If the universe is not entirely homogeneous at large scales, as once believed, but exhibits regional differences in physical laws, densities, or rates of time, then the rules we use to model the cosmos may only apply locally, not universally. This could mean that our observations are shaped by where we are in the universe, making some phenomena appear impossible simply because we are interpreting them through the wrong frame of reference. Such ideas are no longer considered fringe. In light of Webb's findings, respected physicists are revisiting proposals such as varying constants of nature, alternate dimensions, or even the possibility that we are observing imprints from previous cycles of the universe's existence. These theories were once confined to the edges of scientific discourse, but they now serve as potential avenues to explain the growing body of anomalies that do not fit within the conventional cosmological narrative. There is also the question of time itself. Our understanding of time is tied closely to the structure of space and the expansion of the universe. Yet some researchers are now entertaining the notion that time might flow differently in distinct regions of space-time, particularly during the early universe. If time itself was not uniform, then this galaxy may not have formed too quickly at all. It may simply exist in a region where time passed more slowly relative to our frame of observation, creating the illusion of accelerated evolution. This scenario, while speculative, is supported by certain solutions to Einstein's field equations in general relativity, where curved spacetime under extreme energy densities could create time dilation on cosmic scales. It would mean that what we interpret as chronological impossibility is, in fact, a misreading of the temporal geometry of the universe. Such a possibility demands not only new physics, but a new philosophy of observation, where the act of measuring becomes inseparable from the nature of what is being measured. Equally profound are the philosophical consequences. The idea that a single galaxy could upend our confidence in cosmology is humbling. For decades, astronomers believed they were close to a theory of everything, a complete account of how the cosmos works. But Webb's discovery reminds us that the universe does not conform to our expectations. It is not obligated to follow the narratives we construct. Instead, it invites us to listen more carefully, to question more deeply, and to admit that much of what we know may only be partially true. Perhaps the greatest impact of this discovery is that it reawakens the spirit of curiosity at the heart of science. The James Webb Space Telescope has not merely confirmed existing theories, it has defied them. It has forced scientists to confront mystery again, to explore ideas that once seemed too speculative or abstract to pursue. In doing so, it has breathed new life into theoretical physics, observational astronomy, and the search for meaning in the cosmos. As we look deeper into space, we may find that the universe is not just stranger than we imagined, it is stranger than we can imagine. The initial discovery of a massive, well-structured galaxy so soon after the Big Bang was not an isolated incident. As the James Webb Space Telescope continued its mission, scanning deeper and more broadly across the early universe, it began to uncover additional galaxies that shared similarly perplexing characteristics. These were not statistical outliers or one-off anomalies. They were part of an emerging pattern. One by one, the telescope revealed a population of ancient, highly evolved galaxies that appeared to exist in a cosmic era when such complexity should have been impossible. Some of these galaxies exhibited even greater mass and luminosity than the first. They were not the scattered, formless clouds of dust and gas that traditional models predicted. Instead, they bore signs of internal organization, defined star-forming regions, rotational symmetry, and in some cases, bar-like structures typical of mature spiral galaxies. Their existence suggested that the early universe was not merely a chaotic realm of elementary particles and primitive stars. It was, in select locations, a stage already hosting actors with advanced roles in the cosmic play. Perhaps most unsettling was the frequency with which these galaxies were being detected. As Webb expanded its reach across multiple deep fields, the number of such anomalies grew. They were found at various points across the sky, separated by vast distances but clustered in time within the universe's first few 100 million years. The statistical probability of encountering so many of these galaxies by chance became vanishingly small. This meant that either our observational methods were fundamentally flawed, or the universe itself was far more diverse in its early structure than previously believed. The growing sample also allowed astronomers to examine broader trends. Many of these galaxies were chemically enriched, with detectable quantities of elements such as magnesium, silicon, and even trace amounts of platinum, elements that require several generations of stars to be produced and dispersed. Such findings made it increasingly difficult to cling to conventional timelines. The early universe, according to Webb's observations, had somehow managed to accelerate processes that were thought to require billions of years. Either the laws of stellar evolution need to be redefined, or something else entirely was driving this cosmic maturation. Moreover, these galaxies did not exhibit the expected signs of violent collisions or gravitational disturbances that usually accompany rapid growth in cosmic structures. Their forms were remarkably intact, lacking the tidal distortions and stellar trails typically left behind by merging events. This suggested that they had developed in relatively stable, isolated environments. Again, contrary to the standard view that early galaxies formed through frequent chaotic mergers. If such pristine conditions existed in multiple regions of the early universe, then the large-scale structure of the cosmos may be far more variable than currently understood. As data continued to pour in, some researchers began to hypothesize that these galaxies might be forming through an entirely different mechanism, one that bypassed the long sequences of hierarchical buildup predicted by standard models. One bold proposal suggested that certain regions of the early universe could have experienced conditions of extreme density and temperature, allowing for a kind of fast-track galaxy formation. These regions might have hosted unusually efficient star formation rates, enhanced gravitational coherence, or even unknown interactions between matter and dark energy. Others turned to the idea that the galaxies being observed were not merely early, but had somehow experienced time differently. If space-time itself is not homogeneous, if, under certain conditions, time can flow at different rates, then it is conceivable that these galaxies evolved over what felt to them like billions of years, even while only a few 100 million years passed in the larger universe. This notion, grounded in general relativity, is highly speculative, but cannot be ruled out given the data Webb continues to provide. Supporting this speculation, Webb also detected faint signals of what might be gravitational interactions, unlike any previously modeled. In some galaxies, the distribution of mass and light implied internal dynamics, driven by forces not accounted for by ordinary matter or traditional dark matter halos. These signatures prompted a renewed interest in exotic forms of matter, such as warm dark matter, self-interacting dark matter, or even hypothetical particles that interact gravitationally but evade detection through other means. If such entities exist, they could help explain both the speed and orderliness of early galactic growth. Intriguingly, a subset of these galaxies showed synchronized waves of star formation, patterns that moved across galactic disks as if responding to a common trigger. These patterns were too coherent to be explained by internal feedback loops or local gravitational interactions alone. One theory proposed the existence of a background quantum field, a kind of cosmic metronome that could influence regions across vast distances, creating rhythmic pulses of energy that catalyzed star formation. Though highly speculative, this idea reflects a growing sense that the early universe may have been governed by forces or phenomena not yet fully understood. Another possibility is that some of these galaxies are composite illusions, created by gravitational lensing. In such cases, massive objects between Earth and the distant galaxy can warp space-time and magnify the light of background objects, sometimes even overlapping multiple sources into a single image. However, detailed modeling of these anomalies suggests that lensing cannot fully account for the stability, symmetry, and chemical makeup observed. The galaxies appear to be real, discrete systems, not optical artifacts. In response to these findings, astronomers began combing through data from earlier missions, Hubble, Spitzer, and even ground-based observatories, to search for missed signals. Retrospective analyses revealed that some signs of these early massive galaxies had indeed been present, but were dismissed as statistical noise or misidentified due to limitations in resolution. It was not that Webb had revealed something entirely new. It had simply shown us what we had been unable, or perhaps unwilling, to see before. This realization has sparked a methodological reckoning. Algorithms that once filtered out anomalous data are being revised. Astronomers are beginning to consider that their tools and models might be too tightly bound to existing paradigms, designed to confirm what is already believed, rather than to discover what lies beyond. With Webb, science is now entering a more open-ended phase, where observation leads and theory must follow, even if that means abandoning long-held certainties. Perhaps the most exciting implication of these discoveries is their impact on the search for life. If galaxies were forming earlier and with a greater abundance of heavy elements, then rocky planets, and potentially life, could have emerged far sooner than we imagined. Some scientists are beginning to view these ancient galaxies not merely as astrophysical puzzles, but as possible cradles of long-lost biospheres, or even civilizations that rose and fell before our solar system was ever formed. In this context, Webb's mission is no longer just a survey of stars and galaxies. It is an act of cosmic archaeology. Every pixel of light it captures is a fragment of history, a fossil etched in the fabric of space. As its observations accumulate, they tell a story not of a slow, predictable universe, but of one that is rich, variable, and filled with surprises. A universe that challenges us not simply to measure it, but to understand it in a deeper, more creative way. As the James Webb Space Telescope continued to deliver data that defied every theoretical boundary, the scientific community found itself in a rare position, forced to explore ideas that had long been considered too speculative, too radical, or too incompatible with accepted frameworks. What had begun as a single anomaly was rapidly growing into a pattern of contradiction. The early universe, once believed to be a slow and gradual story of structure formation, was now presenting evidence of complexity, maturity, and precision at a time when chaos should have reigned. To account for this mounting body of unexpected observations, theorists began entertaining alternative models that pushed the edges of modern physics. One of the first serious proposals centered on the possibility that dark matter, an invisible substance believed to make up over 80% of the universe's mass, may not be as passive as previously assumed. In standard models, dark matter acts as a gravitational scaffold, guiding the formation of galaxies. But what if, in the early universe, dark matter interacted more directly with ordinary matter, transferring energy or accelerating star formation through as-yet undetected processes? This concept, known as self-interacting dark matter, proposes that dark matter particles may occasionally collide, exchange momentum, or decay in ways that influence their surroundings. If true, then galaxies could have formed more quickly and more coherently in regions with concentrated dark matter activity. Such a scenario would not only explain the sudden appearance of mature galaxies, but also the stable rotation curves and dense central structures observed in Webb's earliest detections. Laboratory tests and collider experiments are now being designed to search for indirect evidence of these interactions. Another radical hypothesis involves modifying the laws of gravity themselves. General relativity, Einstein's crowning achievement has successfully described gravitational phenomena for over a century, yet it has rarely been tested in the extreme conditions of the early universe. Some theorists now suggest that gravity may not behave the same way on cosmic scales or during epochs of high energy density. In these modified gravity models, such as MOND, modified Newtonian dynamics, or emergent gravity, galaxies can form faster and more efficiently, even in the absence of dark matter. These ideas, once relegated to the margins of astrophysical theory, are gaining renewed interest as Webb's findings continue to undermine traditional models. Modified gravity could potentially explain not just the existence of early galaxies, but also the inconsistencies in dark matter distribution, the absence of merger scars, and the synchronized bursts of star formation seen in multiple systems. Still, these theories remain controversial as they challenge the geometric assumptions embedded in general relativity and require new mathematical frameworks to describe spacetime curvature. Some scientists are thinking even more radically, beyond gravity and dark matter, beyond the familiar four dimensions. String theory and its cousin, M theory, propose that the universe may contain additional spatial dimensions beyond the three we experience. These extra dimensions could be tightly curled, invisible to us, but capable of influencing physical processes at large scales. If such dimensions exist, they may allow energy or information to bleed into our universe, seeding early structures or altering the behavior of matter in the formative epochs of cosmic history. This opens the door to higher dimensional cosmology, a realm where galaxies are not merely shaped by local forces, but by interactions with structures beyond our observable horizon. Some models suggest that gravity may propagate through these extra dimensions more efficiently than light, accelerating the clumping of matter and the formation of galaxies in certain regions. Others postulate that what we observe as isolated galaxies might be shadows or projections of more complex, higher dimensional objects intersecting with our three-dimensional world. One of the more provocative theories gaining attention is the idea of conformal cyclic cosmology, introduced by Nobel laureate Roger Penrose. In this framework, the universe is not a one-time event that began with the Big Bang and will end in a cold, entropic future. Instead, it undergoes endless cycles of expansion, decay, and rebirth. Each new universe, or aeon, arises from the stretched-out future of the previous one. If this is true, then the galaxies Webb is observing may be remnants, ghosts from a prior cosmic cycle, preserved through unknown physics at the boundary between aeons. The implications of this model are staggering. It means that the current universe contains imprints from its predecessors, encoded information from a previous cycle that shapes the distribution of matter, the emergence of structure, and perhaps even the physical constants we take for granted. Observations of ancient galaxies rich in heavy elements could be interpreted not as signs of premature evolution, but as evidence of inherited complexity from a universe that existed before ours. While speculative, this idea is grounded in mathematical symmetry and is being actively explored through data from cosmic background radiation. A related proposal involves holographic cosmology, derived from the holographic principle in theoretical physics. This principle posits that the entire three-dimensional universe may be a projection of two-dimensional information encoded on a distant boundary, similar to how a hologram encodes depth in a flat surface. If our universe operates as a holographic system, then what we observe through telescopes like Webb may be manifestations of information, not fixed physical objects. In this interpretation, the early appearance of mature galaxies could be the result of computational distortions or glitches in the way the universe renders its data. While these ideas may seem like science fiction, they arise from serious attempts to unify quantum mechanics and general relativity, two pillars of modern physics that have never been fully reconciled. Webb's data, by challenging both quantum cosmology and classical models, is forcing scientists to look for a deeper, more fundamental description of reality. It is no longer sufficient to describe how the universe behaves. We must now ask why it behaves this way, and whether our observations are truly objective or filtered through a framework we do not yet fully understand. Another intriguing possibility is that of variable physical constants. Constants like the speed of light, the gravitational constant, and the fine structure constant are assumed to be unchanging across space and time. But what if they are not? If even one of these constants varied slightly in the early universe, the effects on galaxy formation, star life cycles, and matter interaction would be profound. Current experiments are now examining ancient quasars, gravitational lensing, and deep field spectra to detect possible shifts in these constants over cosmic time. There is also growing interest in the idea of cosmic phase transitions, moments when the universe underwent abrupt changes in its fundamental state, similar to how water freezes or boils. During such transitions, new physical laws might emerge, or familiar ones might behave differently. If one or more of these transitions occurred shortly after the Big Bang, they could have created conditions that allowed for the rapid and orderly formation of galaxies in select pockets of space. These islands of coherence may explain why only some regions exhibit advanced structures while others remain primitive. In the end, these extreme models share one common trait. They reject the notion of a single, smooth, predictable universe. Instead, they embrace the possibility that the cosmos is layered, dynamic, and governed by principles we are only beginning to glimpse. Whether the answer lies in altered gravity, hidden dimensions, cyclic time, or encoded information, one thing is certain. The James Webb Space Telescope has shattered the illusion of finality in cosmology. It has exposed the universe not as a solved equation, but as an unfolding mystery still rich with undiscovered truths. The revelations brought forth by the James Webb Space Telescope did not merely disrupt the field of cosmology. They sent ripples into other scientific disciplines, forcing them to reconsider long-standing assumptions and theoretical frameworks. Astronomy may have been the front line of observation, but the implications of Webb's findings extended into fields as diverse as planetary science, astrobiology, quantum physics, information theory, and even the philosophy of science itself. In each domain, the consequences were not minor revisions, but seismic shifts in perspective. Perhaps the most immediate impact was felt in the study of planetary formation. If galaxies in the early universe contained significant quantities of heavy elements, such as carbon, oxygen, silicon, and iron, far earlier than previously believed, then the conditions for forming rocky planets must also have emerged much sooner. These elements are essential for building terrestrial worlds, atmospheres, and potentially even biospheres. The implication is clear. Planet-forming material may have been available within a few 100 million years after the Big Bang. dramatically accelerating the potential timeline for habitable environments.
This realization brought astrobiology into sharper focus. For decades, the search for extraterrestrial life has been guided by the assumption that life requires billions of years to emerge and evolve. But Webb's discoveries suggest that the ingredients for life could have existed during epochs previously thought inhospitable to biological complexity. If star systems rich in heavy elements formed quickly, then the molecular precursors of life, amino acids, nucleotides, and other carbon-based compounds, may have begun assembling not billions of years ago, but within the first chapter of cosmic history.
Some researchers now speculate that life may have arisen, flourished, and disappeared in ancient galaxies long before our solar system ever formed. These potential ghost biospheres are not merely the stuff of science fiction. They are becoming legitimate objects of scientific inquiry. Astrobiologists are re-examining data once dismissed as noise or artifact, looking for subtle chemical signatures, anomalous light curves, or unexplained patterns in exoplanet atmospheres that might hint at the presence of ancient, now extinct life. The implications also stretch into exoplanet research. The discovery of early metal-rich galaxies implies that planet-hosting stars may have existed for far longer than assumed. This shifts the parameters for what is known as the galactic habitable zone, the region within a galaxy where conditions are favorable for life. If such zones existed earlier and more widely than predicted, the estimated number of habitable worlds across the universe could increase significantly. Moreover, the lifespan of those worlds and the civilizations they might support could span epochs unfamiliar to human chronology. In the realm of quantum physics, Webb's findings have inspired renewed attention toward the relationship between observation and reality. If galaxies appear older than they should be, and their light carries information that contradicts space-time models, then what does it truly mean to observe something across billions of years? The concept of quantum decoherence, how a system transitions from multiple possibilities into a single observed state, gains new depth when the object of observation is not a particle in a lab, but a galaxy from the dawn of time. Some physicists are now exploring whether the act of cosmic observation may itself influence the collapse of informational states at large scales. These developments have also invigorated debates within information theory. The possibility that the universe might be holographic, that space and matter emerge from encoded information on a distant boundary, transforms our understanding of what galaxies even are. If Webb is capturing structured information rather than simply observing physical objects, then the universe behaves more like a computational system than a mechanical one. This reframes questions not just about how the cosmos formed, but why it has structure at all, and whether consciousness plays a role in perceiving that structure. Beyond the sciences, the philosophical implications of Webb's discoveries are equally profound. For centuries, natural philosophy sought to derive order from observation, believing that nature operated according to universal laws accessible through reason and experiment. But when observation itself begins to challenge those laws, it invites a re-evaluation of epistemology, how we know what we know. The early mature galaxies force us to confront the possibility that human models of time, causality, and scale are not absolute, but context-dependent constructs shaped by our position within the universe. This has led to a growing convergence between empirical science and metaphysical inquiry. Questions once considered speculative, such as the nature of time, the origin of order, or the influence of the observer, are now central to interpreting hard data. Philosophers of science are working alongside physicists and cosmologists to develop new frameworks of understanding that can accommodate paradox, uncertainty, and incompleteness, without discarding the rigor of empirical validation. In this light, Webb's discoveries are not just scientific, they are deeply existential. Finally, the James Webb Space Telescope is reshaping how science itself is practiced. The complexity of its data, the subtlety of its contradictions, and the sheer scale of its observations demand an interdisciplinary approach. Astrophysicists collaborate with machine learning experts, quantum theorists engage with cosmologists, and philosophers join teams analyzing data pipelines. The barriers between disciplines are dissolving, replaced by a shared commitment to unraveling a mystery that no single field can solve alone. In many ways, the most transformative impact of Webb's discoveries lies not in the galaxies it has revealed, but in the questions it has raised. It has reminded us that science is not merely a catalogue of known facts, but a living process of inquiry, a journey into the unknown guided by tools that grow sharper with each generation. With every photon captured by Webb, we glimpse not only distant light, but deeper layers of meaning about our place in the universe. And as these revelations echo across disciplines, they serve as a call to think bigger, dig deeper, and imagine more boldly than ever before. The revelations brought forth by the James Webb Space Telescope have not only disrupted scientific theories, they have altered the very manner in which science is conducted. For decades, cosmology operated with increasing confidence, refining models with each new data point. But when those models failed to anticipate what Webb observed, it became clear that a deeper shift was required, not just in the conclusions scientists drew, but in how they approached the process of discovery itself. Traditionally, theory has guided observation. Researchers built models first, then turned telescopes to the skies to confirm them. With Webb, that relationship has reversed. Observation now leads, and theory must respond. The telescope has uncovered phenomena so far outside the boundaries of established thinking that scientists have been forced into a more reactive, exploratory mode, one driven not by prediction, but by explanation. This reversal has sparked a re-examination of foundational assumptions. Core ideas about the uniformity of cosmic time, the behavior of gravity, and the sequencing of galaxy evolution are being reconsidered from the ground up. In many cases, the challenge is not the lack of data, but the frameworks used to interpret it. Theories that once seemed airtight now appear limited, constrained by the perspectives and tools that shape them. A key realization has been the role of bias, especially in data selection. Instruments and software are designed with certain expectations in mind. Anomalies that do not match existing templates are often filtered out or ignored. With Webb's extraordinary sensitivity, scientists now see that some of the most groundbreaking data may have previously been discarded, not because it was incorrect, but because it was unfamiliar. This has led to a methodological shift. Astronomers are rewriting algorithms to search not only for expected patterns, but for deviations. Machine learning systems are being trained to identify the unusual, not just to classify known objects, but to highlight the unknown. In this environment, anomaly has become a valuable signal rather than a statistical nuisance. Discovery now depends as much on openness as on precision. This change has also accelerated interdisciplinary collaboration. The questions raised by Webb's discoveries do not fit neatly within any single domain. Cosmologists work alongside quantum physicists, philosophers, and data scientists to explore implications that stretch from particle behavior to the nature of time. Scientific boundaries are dissolving, not as a trend, but as a necessity. No single field can fully grasp what Webb has revealed alone. Alongside this structural evolution, there has been a transformation in scientific culture. Researchers are increasingly willing to share uncertain findings, propose bold hypotheses, and revisit ideas once dismissed. The pressure to appear correct has given way to a greater value: curiosity. As scientists engage with data that defy their expectations, they are rediscovering that the pursuit of knowledge is not about answers, it is about questions. This spirit of openness is reshaping how scientists communicate and collaborate. Instead of guarding early results, teams now publish preliminary findings and invite public scrutiny. Rather than competing to confirm existing theories, they are building platforms to test new ones. The goal is no longer to protect the boundaries of knowledge, but to expand them, even if that means embracing contradiction, ambiguity, or revision. Even the language of science is shifting. Terms like impossible, anomalous, and unexpected are no longer viewed as threats to credibility, but as invitations to inquiry. Scientific vocabulary is evolving to accommodate complexity, nuance, and uncertainty. In doing so, science becomes more than a tool for problem solving. It becomes a way of engaging with a universe that does not always yield to logic, yet always rewards humility. The James Webb Space Telescope has done more than observe the universe. It has held up a mirror to scientific practice. It has reminded us that knowledge is provisional, that models are maps, not territories. And most of all, it has rekindled a scientific mindset, rooted not in control, but in wonder. In the face of a cosmos that continues to surprise us, the most powerful response may not be to explain, but to explore. The discoveries made by the James Webb Space Telescope have reshaped not just our scientific understanding, but our place within the cosmos. What began as a search for ancient light has led to questions about time, structure, and the very fabric of reality. We once believed the early universe to be simple, primitive, yet Webb revealed a cosmos rich in complexity and contradiction, long before it should have been. These revelations do more than challenge physics. They invite us to reconsider how knowledge itself is formed. The universe is not a completed puzzle, but a living, shifting mystery. Each new image is both a window and a mirror, offering not only a glimpse into deep space, but also a reflection of our own assumptions, limits, and ambitions. Philosophically, Webb's mission reminds us that certainty is temporary and that wonder is essential. In trying to map the stars, we may find that the truest discoveries lie not in final answers, but in the courage to keep asking deeper questions. Perhaps the cosmos is not merely vast, it is fundamentally unknowable, and that unknowability is what makes it endlessly worth exploring. In the age of powerful machines and precise equations, the most profound gift of the universe may be its refusal to fit inside our expectations. And that is not a failure of science, it is its heartbeat.
If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.